Okay, so let's get to the second part of this lecture. So in the first part of this lecture, we discussed the fundamental theorem of arithmetic, which states that every integer can be uniquely factored into a product of prime numbers. So we discussed what prime numbers were. We discussed this unique factorization property, but we didn't prove the fundamental theorem of arithmetic. And then we discussed some ways to check whether numbers are prime, and we showed that there are infinitely many primes. So that is definitely kind of one of the high points of this whole chapter on number theory and modular arithmetic. So we're going to skip over a lot of the sections in the book which involve the conjectures, like the Goldbach conjecture, the twin prime conjecture, and the Mersenne prime stuff. We're going to skip over a lot of that and go directly to GCD. So GCD is another part of studying integers, and in particular, the relationships of integers with each other. So one of the most basic relationships that we can ask about a pair of integers is, does one divide the other? But there's a more subtle or more interesting property that you can talk about, which is called the greatest common divisor. Okay, so definition. The GCD is going to be the largest integer that divides two integers. So given A and B integers, and let's for the moment say A and B are not equal to 0, then the GCD of the pair A and B is going to be the largest integer D, such that D divides A and D divides B. Okay? So let's start off just by getting some examples in. As an example, let's try to find the GCD of 100 or 101 and 100. So one of the things that I could start asking is, what exactly are the divisors of each of these numbers? Well, 100 is divided by plenty of things. It's divided by 2, it's divided by 5, it's divided by 10, it's divided by 20, 25, 4. 100 is divisible by a ton of things. How about 101? 101, as we checked previously in this same lecture, is actually prime. So its only divisors are 1 and 101. So if I'm looking for some D that divides both 101 and 100, but my only options for dividing 101 are 1 and 101, then indeed the GCD of this pair has to be 1. There's no number greater than 1 which no integer greater than 1 which divides both 100 and 101. Okay, so this is a fairly reasonable thing. So essentially, you can test, well, I don't want to say that right now. Let's do a slightly more involved and interesting example. Let's talk about the GCD of 1,000 and 625. So my first process for trying to find the GCD is, once again, not the fastest process, but a kind of naive process, which is I want to find the prime factorization of each of the numbers involved. And using that prime factorization, it should be quite easy for me to see what the GCD is. So what's the prime factorization of 1,000? Well, 1,000 is 10 times 10 times 10. I know the prime factorization of 10, it's just 2 times 5. So really, this is the GCD, on one hand, of 2 cubed times 5 cubed. And then I can look at the GCD of 25, or 625. And it turns out that 625 should be 5 to the 4th. One way to kind of think about this is, first of all, 625 is divisible by 5 because the last 2 digits are divisible by 5. So notice that that's a rule that only works for 5s, by the way. You can't say that something's divisible by some arbitrary number just because the last 2 digits are divisible. But for 5s, it works. So 625 is divisible by 5, and if you divide that out, it'll be 125. And 125 is 5 times 25. So if I make this little tree, 625 is equal to 5 times 125. But 125 is equal to 5 times 25. And 25 is equal to 5 times 5. So you've done this before, probably in elementary school. So 5 to the 4th. And now what I'm looking for is the largest number that divides both of these. And the point is that I can read this off easily from the prime factorizations. 5 cubed divide, so any number that I make by products of these primes such that the powers on the primes are less than or equal to 2 or 3 and 3 will divide this number, right? 2 times 5 will divide this number, 2 will divide this number, 2 squared times 5 cubed will divide this number, etc. And in particular, 5 cubed divides this number. Also, 5 cubed divides this number. 125 does indeed divide 625. So here I see pretty quickly that the GCD is equal to 5 cubed, which is equal to 125. Okay? So the point is that GCD is a relationship between 2 numbers, which is a little more subtle and a little more involved than one number dividing another number. In particular, if I take the GCD, let's examine what happens in some examples. If I take the GCD of 2 numbers such that one number divides the other number, let's see what we get. So for instance, why don't I take the GCD of 7 and 14? Well, according to the prime factorizations, the GCD, since 7 divides 14, well, the prime factorization is just 7, and here the prime factorization is 7 times 2. The point is that when one of the numbers divides the other number, then its prime factorization appears as some, how shall I write it? Every prime that appears in the first number will appear in the second number to a lower or possibly lower power. So for instance, since 7 divides 14, 7 to the 1 also appears, like there's a 7 to the 1 in 14. Maybe I should do a more interesting example. Let's look at the GCD. So in any case, this is 7. Now let's think about the GCD of 7 and something like 98. This is the same thing as the GCD of 7, and this is 7 squared times 2, right? 49 times 2 will give me 98. So once again, I see that the prime factorization of the number that divides the other, like all of your primes appear in the primes of the larger number, and all of the powers of the primes over here are less than or equal to the powers of the primes that appear over here. So once again, this is just 7. So one way to think about divisibility using GCD is one number divides another number if the GCD of the pair is one of the numbers. That's something that I encourage you to try to prove yourself. But the point of this discussion is just to show that GCD is a more subtle and more interesting question to ask of a pair of numbers than just, does one number divide the other number? Let's do one more example. So let's look at the GCD of 6 and 77. Once again, I can very quickly do the prime factorization of these numbers. This is the same thing as the GCD of 2 times 3 and 7 times 11. So notice these two numbers share no primes in common. So the only possible number that could divide both of these is equal to 1. Because any number that divides either of those numbers has to have at least one prime factor in common, right? What divides 6? Well, 1, 2, 3, and 6. What divides 77? 1, 7, 11, and 77. Since none of those are the same besides 1 is the only thing that I can put for the greatest common divisor. Okay, so with this in place, I can make a definition. And I'll try to find a better. So definition. Two numbers A and B. A and B in Z are called relatively prime if their GCD of A and B is equal to 1. Right? So what this is saying is that relatively prime means that these two numbers share no prime factors. When I write A into its prime factorization and I write B into its prime factorization, no primes appear on both lists. Because if a prime appeared on both lists, then that prime would divide both A and B. These two numbers are called relatively prime. Notice that here, these two numbers, 6 and 77, are relatively prime with respect to each other, but neither of them are actually prime, as we see from the prime factorization. Both of them are actually products of primes. Both of them are composite, but they're still relatively prime with respect to each other. So relatively prime is a notion between a pair or a collection of numbers, whereas prime is a more absolute notion. Okay. And we can slightly expand on this definition. Another definition. A finite collection of integers say A1, A2, all the way up to AN, is called pairwise relatively prime. If I take any pair of them and I examine their GCD and I get 1. If the GCD of AI, AJ is equal to 1 for all I not equal to j in 1 through n. Right, so essentially, one way to think about this is you take some collection of numbers, and each number is broken down into its prime factorization. So it's like bringing some amount of primes to the table. And the collection of integers is called pairwise relatively prime if each of them are bringing totally distinct collections of primes to the table. So let's do some examples. Are 14, 17, and 21 relatively prime, or pairwise relatively prime? Well, no, because if I look at their prime factorizations, I've got a 2 times 7, I've got a 17, and then I've got a 3 times 7. So that is the GCD of 14 and 21 is not equal to 1. So this collection is not pairwise relatively prime. Whereas if I take some collection that looks like 7, 8, 11, and 9, this is pairwise relatively prime. I've got a 7, I've got 2 cubed, I've got 11, and I've got 3 squared. So each of these is bringing different collections of primes to the ensemble, so to speak. So these are pairwise relatively prime. Okay, so we want to explore some more properties of this GCD relationship, or this function, really, function on a pair of integers. Okay, so as I mentioned before, now I can kind of do it a little more rigorously. One method of finding GCDs of some numbers, let's work with a pair. Actually, I mean, it can be done more generally than a pair, but one way to find the GCD of a pair of numbers is to find the prime factorization of those numbers. Prime factorizations of all numbers involved, of that pair. So I just want to show you an example of what's going on here. Let's take the following collections of numbers. Let's say that I'm trying to find the GCD of 2 cubed times 5 squared times 7 to the 4th times 11, and the GCD of 2 times 5 to the 4th times 7 squared times 13 times 17. Okay, so what I've done is I've just listed off some numbers just by reading off their prime factorizations. And from the prime factorizations, I can go through and check, does 2 divide both of these numbers? Yeah, because the 2 appears here and here. Does 5 squared divide both of these numbers? Yeah, it goes through here and here. Does 7 squared divide both? Yes. Does 11 divide both? No. There's no 11 over here, and similarly, there's no 13 or there's no 17 over here. So what I'm going to do is I'm going to take all of the primes that are involved, and I'm going to write these numbers as some product of all of the primes. So in particular, 2 cubed times 5 squared times 7 to the 4th times 11, well, it is this, but it's also equal to times 13 to the 0, so I'll put the powers everywhere, times 17 to the 0. So I've written this number in terms of all of the primes that appear, but some of the primes may appear to the 0th power, right? 13 to the 0 is 1, 17 to the 0 is 1, and I haven't changed this number. I've just listed all the primes that I could possibly be dealing with. And second of all, this number is equal to 2 to the 1 times 5 to the 4th times 7 squared times 11 to the 0 times 13 times 17. Once again, I'm just writing this number in terms of all of the primes that I need to consider. Then the GCD of these two numbers is going to be look through every prime and take the minimum of the powers in each case. So the GCD of these numbers is going to be, well, I look at the first prime that appears, and I take the lowest power. So it's going to be 2 to the 1. No higher power of 2 divides both of these numbers. Then I move over to the next prime. 5 to the 4th appears here, 5 squared appears here. I take the smaller power, times 5 squared. No number with more than 5 squared can divide both of these numbers. Now I look at sevens. Once again, the minimum comes from over here. So I put a 7 squared here. No number D with a prime factorization that involves more than 2 7s could possibly divide both of these numbers. Next, I look at 11. The smallest is 0, so I'm going to have 11 to the 0. Here I have 13 to the 1 and 13 to the 0, but now I'm just going to have 13 to the 0 because that's the minimum of these two powers. And lastly, times 17 to the 0. Right? The point is, if any number has some higher power, some like 13 or 13 squared or 13 cubed, it cannot possibly divide this number. And it also can't divide this number. So once you have the prime factorizations, you can read off the GCD just by taking the minimums of each of the primes that possibly appears. So GCD is equal to 2 times 5 squared times 7 squared. That's the GCD of these two numbers. So more generally, if we write A is equal to P1 A1 times Pn An, and I write B is equal to P1 B1 all the way up to Pn Bn, where the set P1 all the way up to Pn consists of all primes in the factorization of A or B. Right? So here what I'm saying is take all the primes that possibly appear, list them out, and then write A in terms of P1 to the A1 all the way up to Pn to the An, where some of these Ans might be 0, and some of these Bns might be 0, right? Like this. I'm writing out this number in terms of some prime to the 0 times some prime to the 0. And similarly over here, I've got some prime to the 0, some prime to the 0, some prime to the 0. But once I have written my two numbers in this fashion, in a kind of semi-prime factorization, right? This isn't unique because I've got 1s appearing. But once I've written my two numbers this way, then the GCD of A and B is equal to P1 to the minimum of A1 and B1 times P2 to the minimum of A2, B2, all the way up to P to the N times the minimum of AN, BN. Okay? So what I'm pointing out here is that we have a nice expression for the GCD in terms of the prime decompositions of the two numbers that we're interested in. Okay? So there's another interesting number that we can associate to a pair of numbers. So here we took a pair of numbers, a pair of integers, and we associated the greatest common divisor to that pair. There's another interesting number that we can introduce called the least common multiple. It is not great, I know. Okay, so by definition, the LCM of A and B is the smallest possible positive integer that is divisible by both A and B. The LCM of A and B in Z is the smallest integer which is divisible by A and B. So the GCD involves looking for numbers which divide A and B. The LCM is done by considering integers which are divided by both A and B. So there are some very quick examples that we can start off with. Let's take two numbers which divide each other. So let's look at the LCM of 4 and 8. So I'm looking for the smallest number such that 4 divides that number and 8 divides that number. Well, 4 divides 8, so really this is only asking what is the smallest integer which is divisible by 8. Well, I'm sorry, I'm not in a frame. And that number is 8. 8 is the smallest number such that smallest integer, which is divisible both by 8 and 4. So when one number divides another number, we expect the LCM to be that larger number, the one which is divided by the other one. Let's do some more examples. Let's look at the LCM of, what do I have? 35 and 16. Okay, so what I'm asking for is some number which is divisible by 35 and divisible by 16. Once again, my tool in my arsenal is going to be the fundamental theorem of arithmetic. I'm going to be able to write each of these numbers uniquely as a product of primes. So here, what I'm really looking for is the LCM of 35, which is 5 times 7. Is that true? 21, 28, 35. Yes. 5 times 7. And 16 is 2 to the 4th. So what I need to do here is I need to find some number which is divisible by 2 to the 4th, which means its prime factorization has 2 to the n, where n is some number greater than or equal to 4. And it also needs to be divisible by 5 and 7, which means its prime factorization has to include a 5 and it has to include a 7. The smallest such number is indeed the product of all these numbers. This LCM is going to be equal to 2 to the 4th times 5 times 7. If I look for, I can't remove any of these numbers from the prime factorization of the LCM, because then it wouldn't be divisible by one of these numbers, and it's the smallest possible. I don't have any higher powers or other primes. So in particular, when two numbers are relatively prime, the LCM is just the product of those two numbers. This is something that you will, well, it'll be easy to prove a little further on, but you'll do some homework involving this way of thinking about the LCM. Let's do one last example. Well, not one last, but one more. Let's consider the LCM of, now I'm going to make up some numbers, say 2 to the 4th times 5 squared times 7 times 11 cubed. And then over here, I'm going to have 2 to the 7th times 11 times 13. And just kind of pull these numbers out of the hat. So I need some number which is divisible both by this number and by this number. The point is, if I have some number which is divisible by both of these, then first of all, it needs to be divisible by any of the, like if a number is divisible by this whole thing, it's certainly divisible by 2 to the 4th or 5 squared or 11 cubed. This is by our divisibility theorem that we did in the previous lecture. If A divides B and B divides C, then A divides C. So I'm looking for some number which is divisible by this thing, which means it's certainly divisible by 2 to the 4th. And I also know that it needs to be divisible by 2 to the 7th. So a reasonable first condition that I look for is that my number should have a 2 to the 7th involved. Because then it's divisible by 2 to the 4th, and it's also divisible by 2 to the 7th. Let's consider 5s. the least common multiple of these two numbers must be divisible by 25. There's no 5 appearing here, so it doesn't really impose any condition. Like being divisible by this number doesn't mean that you're divisible by 5, but being divisible by this number means that you're divisible by 5 squared. So I need a 5 squared appearing in my least common multiple. I think you're starting to see the pattern. I need to also be divisible by 7. I need to also be divisible by 11 cubed. And I also need to be divisible by 13. So this number is the number that appears when I write down all of the primes in the prime factorization of both of these numbers, and I take the maximum of each one, right? 2 to the 7th, this 7 is the maximum of 2 to the 4th and 2 to this, and of 4 and 7. This 5 squared, this 2 appears because if I look at the number of 5s appearing here, there are 2 of them. And I look at the number of 5s appearing here, there are 0 of them. So here I'm taking the maximum of 2 and 0, I get 2. A 7 appears here, no 7 appears here, so I take a 7 to the 1. 1 is the maximum of 1 and 0. Similarly, if I look at 11, 3 11s appear over here, only 1 appears here. I take the maximum, I get 3. And then here I'm taking the maximum of 1 and 0, I just get 1. Okay? So what we are getting here is that the LCM of A and B, what you should do is you should write out A and B as we did before. Write out A is equal to P1 to the A1 times Pn to the An, and B is equal to P1 to the B1 all the way up to the Pn to the An, or Bn, where P1 through Pn are all primes appearing in the prime factorization of A or B. And notice that some of the ANs, or the AIs, could be 0, and some of the BIs could be 0. For instance, if I'm writing this out for this number as a product of all the primes that appear, this is 2 to the 7th times 5 to the 0 times 7 to the 0 times 11 times 13, right? So zeros can appear. But once we have written out our A and B in terms of all the possible primes that we need to take care of, the LCM is equal to P1 to the max, A1 and B1, P2 to the max of A2 and B2, all the way up to Pn to the max of An and Bn. So this is a kind of a parallel description between the GCD and the LCM of two numbers. And from this description of the LCM, we get a very nice corollary. Is that if we take two random numbers, A times B will automatically be equal to the GCD of A and B times the LCM of A and B, right? Because what is A times B? Well, what you should first do is write out all of the primes that can possibly appear in A and B, and then A times B is equal to P1 to the A1 plus B1 times P2 to the A2 plus B2, all the way up to Pn to the An plus Bn. Right? If I write out A like this, and I write out B like this, and then I multiply them together, all I do is I add the exponents. And then on this side, I check what is the GCD equal to. Well, the GCD is equal to P1 to the min, A1, B1, all the way up to Pn to the max, or sorry, Pn to the min, An, Bn, times, now I do the LCM, P1 to the max, A1, B1, times Pn to the max, An times An and Bn. And now I add the minimum of A1 and B1 to the maximum of A1 and B1, and I'll get exactly A1 plus B1. Similarly, if I add the min of An and Bn to the max of An and Bn, I get exactly An plus Bn. This process maybe looks a little complicated, and it does have a lot of notation, but if you just start writing out prime factorizations, if you did that with this example, you'd see it's exactly true. And in fact, I have 41 seconds, so I can try to do it with this example. So all that this corollary is saying is that if I take the product of these two numbers, so A times B is equal to 2 to the 7 plus 4 is 11, times 5 squared, times 7, times 11 to the 4th, times 13. This is going to be exactly equal to, well, first the GCD, which is 2 to the 4th times nothing times 11. This is the GCD. This is the mins of all things that appear, times the max of everything that appear. 2 to the 7th times 5 squared times 11 cubed. Oh, I need a 7. Times 11 cubed times 13. And indeed, it works out beautifully. That's all that this corollary is saying.